So in this video, we are going to study the domination relation that is used for the register promotion and optimization in more details. So in the previous video, we studied the register promotion and its key ideas and a little bit about the algorithms, but left many details on domination relation in a later slide. So this is the later lecture video that is explaining the domination relation used for the register promotion optimization. Okay, let's start with definition. So what is the domination relation? So you're given a directed graph G and the initial vertex I. So this is basically conceptualizing the counterflow graph where each block is a node or vertex and the initial vertex I is the starting point, initial block basically. So in this graph and the initial vertex I, a vertex A dominates B if all passes from I to B visits A in between. So there is I, initial vertex I, and this is B, and every pass from I to B should visit A between I and B. So if you can visit B without visiting A, then A does not dominate B. So otherwise, if it is the case that all passes, if you visit B and you should have already visited A in between, then it is the case that A dominates B. And let's assume this notation here, where dom B is the set of dominators of B. It is the set consisting of vertices A that dominates B, basically. So this is the set of the dominators of B, basically. So this idea is applied in CFG. So CFG is itself a directed graph. So you can immediately define the domination relation among the blocks. But in addition, we can say that in KAIST IR and well-known compilers, internal IRs, such as Clang's IR or the GCC's IR, it is the case that all definitions of a register, say X here, is dominating all its uses. So in the IR. So the motivation here is that in order for the uses of registers to be valid, the value should have been defined already previously, and that's the reason why it should be defined before it is used. So that's the reason why we require that a definition dominates all its uses, so that at the time that the register is used, the register has already been defined previously. So that's basically the application of domination relation to the counterflow graph abstraction of the basic blocks. So far, so good. And in addition, in order for streamlining the algorithms on domination relation and CFG, we assume that the initial vertex I has no inbound edges. So in other words, the initial block of a function has no inbound edges. There's no block that is jumping to the initial vertex I. That's the additional assumption we are making here. As I said, the motivation here is simplifying the algorithms. If the initial block I has the inbound edges, the algorithm is become a little bit complicated, as we will see. But yeah, this is just a motivation. And this assumption is actually true in KAIST, CFG, and other well-known compilers IR as well. And this is satisfied by the IRGen of KAIST, in which the initial block is only initializing allocation, and it is jumping to the first instruction of the function, and it is preserved by optimizations. So basically, all the optimizations are transforming a given IR into the output IR. And it is guaranteed that this property, the initial vertex I has no inbound edges, is preserved among the optimizations. Okay, so far so good. And this domination relation has a very good properties like this. The first one is that this is transitive. In other words, if A dominates B and B dominates C, then A in turn will dominate C always. So this property is called the transitivity of this domination relation. If A and B are in the domination relation and B and C are in the domination relation, then A and C are also in the domination relation. The second property is a little bit more difficult to grasp, and it is much more interesting than other properties. So it is saying that for any block that is not the initial one, so this is the vertex that is not the initial one, there uniquely exists another block A that the dominators of B is the union of A and the dominators of A. So in other words, for any B that is not the initial one, there should be something that is called the immediate dominator, or the smallest or the closest dominator, which is A. That A is actually dominator of B. So that's the reason why A is in the set of the dominators of B. And furthermore, the other dominators of B should be the dominators of A. So this equality relation is saying that dominator of B is consisting of two things. The first one is A itself, and the other is the dominators of A. So A is in this way, in this sense, the canonical immediate dominator of B. So that's the reason why we call it immediate dominator and define idom such a function. So idom B is such A that is satisfying this property for B here. So yeah, using this idom, we will calculate this idom relation very efficiently in the later slides. So please draw some graphs and see whether these two properties are actually holding. So see any graph, any realistic directed graph that is resembling some counterflow graph with initial vertex I, and see if this transitivity and the immediate dominator property is actually holding for your graphs. So property 2 looks a little bit dense, and it has some mathematical symbol that is not entirely transparent for most of you. So please draw and see what's happening here. So example is always important and easier to study some mathematical properties. So let's learn by example. So draw it and see it. And we will not prove this property in this class because this class is not about some compiler theory or the mathematical theory about computation or programming, but about compiler construction. But I strongly encourage you to look for proof of this, why this is true, mathematically, rigorously. So, yeah. And using the idom definition, we are going to present the construction algorithm of this domination relation. So domination relation is usually represented as a domination tree on which a DOM tree is a tree in which the parent of a node A is the idom we just defined in the previous slide. So we are going to use this definition to simplify the construction algorithm. So A is here if B is the parent of node A in this DOM tree, that means B is the immediate dominator of A here. And for this DOM tree, we are going to use this equation here to construct the DOM tree here. So this means that, okay, so basically in construction of this DOM tree, the only thing we need to do is getting the value of idom for each vertex. And we have this equation. The immediate dominator of X should be the the list element of the item of y, where y are the predecessor of x in the graph G. So this spread, let's say that this spread is a set of predecessors of x in G here. So predecessor means there is a edge from y to x in G. So y is a predecessor means there's an edge from y to x here. And the immediate dominator of x should be the list of the dominators of the predecessors of x. So this is the property we have for the dominator tree. And again, please draw some example graphs that is realistic counterflow graph, and see if it is actually the true. So we will not prove this property in this course, but I strongly encourage you to understand this property by actually drawing some examples. And you will immediately see, oh, this is actually true. This is quite plausible. And I want you to grasp such an idea that, oh, this is a plausible equation. And only after grasping such an idea, you can confidently implement your optimization in your homework. And here, this list element here is the order according to the DOM tree order. So for two elements in two vertices in the graph, A is less than or equal to another if A is the parent or the parent of parent of, or parent of parent of parent of B, and so on. So this relation is representing the fact that this order relating to this list element is the domination tree's parent-child relation order. Parent is less than or equal to the children in this square order. So you're going to use this equation to construct the item array or the domination tree. So the naive algorithm will be repeatedly refining the items until none is changed, basically. So you are having a recursive the equation here. You are defining item using item. So this is a recursive equation. So item is occurring at the left and right at the same time. So in order to solve this equation, you're going to iteratively increase the potential solution until you reach the equation here. So you are going to begin with the array of items with everything is uninitialized, or you don't know anything concrete about the item, and you're going to increase your potential solution by using this equation. So if you calculate this for your given potential solution, and you incorporate this with your original solution, so that you get a little bit a better solution until you reach this equation. So we are going to see the code for this, and I just want to deliver some idea for high-level idea for the algorithms for this. And the high-level idea is just repeating, updating the item array until nothing is changed. So this is basically an iterative algorithm for getting the item. And it is known that a more sophisticated algorithm will give you a better algorithm in the time complexity. So you can compute this using the linear time of the number of edges here. It is discovered about 20 years ago. But the details of this algorithm will be beyond the scope of this course, because this course is aims to construct a simple compiler rather than the most sophisticated compiler in the world. So for the purpose of this course, it is sufficient to just calculate this item array using a naive iterative algorithm rather than a very sophisticated algorithm. But if you're interested, please search for this, the domination construction algorithm, Elstrup, Harrell, Lauritsen, and 1999, and it will pop up some paper that is describing this very sophisticated algorithm. So if you're interested, please read it. Okay, so I'd like to explain a little bit digression of this domination relation construction algorithm, which is the reverse post order of the graph traversal. So it is accidentally explained by Eli Bendersky's blog post, where the why RPO is good for the purpose of data flow analysis used for the compilers in particular. So this post order is basically a graph traversal strategy. If you already know about the pre-order or post-order or in-order, yeah, it is the same. So it is post-order where you mark a node after all its descendants are traversed. So you only after all the descendants are traversed, you mark the node, and the mark order will be the post order. And it is called the post order because you're going to mark the node after its descendants are traversed. Okay, this is the post order, and you are going to think of a reverse post order. That is basically the reverse of the post order traversal of a graph. So probably this post order is learned in an earlier course about algorithms and data structures. So I'm not going to details about this post order, but if you are curious about the details of this post order, I would like to recommend you to read this blog post here, Eli Bendersky's blog post here. And this RPO has a very good properties. So the first property is that if A dominates B, then we know that A is before B in the reverse post order. So here's some proof sketch I can think of. If A dominates B, then when pushing B to the stack in the post order traversal, then A should have already been put in the stack. That's because A dominates B, and it should not have been put because the traversal of B is not finished. So A is still in the stack, and A is not marked yet. And that's the reason why B is before A in the post order, and conversely, A is before B in the reverse post order. So basically, that's the high-level explanation of this property. And the second property is that if G has no cycles, so G is acyclic, and there is an edge from A to B in G, then we have that A is before B in RPO. So the proof is almost the same with the above. So if when pushing B to stack in the post-order traversal, we know that A should have already been put in the stack because you cannot reach A from B, and in order to reach B, you should have already visited A in between. So that's the reason why B is before A in the post order, and conversely, A should be before B in the reverse post order. So these two properties are mathematical properties, and it has a very good implication to the algorithms for this naive iterative algorithm for calculating the domination relation here. So the property A guarantees that this RPO is used in this way. When you update the IDOM array here, you're going to iterate through all the vertices, right? And you're going to visit the vertices in the reverse post order. So the reason is that the first element to visit is likely to dominate all the other things. So when you update the first element first, then the effect of this update will immediately be reflected on the other elements as well. So that's the reason why we iterate through the vertices in this reverse post order. So it is not guaranteeing. I mean, the use of this reverse post order doesn't increase the precision or the correctness of the algorithm, but it will improve the convergence. So you're going to iterate less than the usual if you visit the vertices in this reverse post order in the calculation of domination tree here. So as I said, the main reason is that if A is visited first here, then its result will likely affect the computation for B here. And that's the reason why B will have a more latest or more precise value on of the IDOM. And as a result, it will shorten the iteration of the computation for this IDOM. So that's the reason why we visit the elements in this reverse post order. Okay, so that is the first benefit of these two properties. So it will populate IDOMs much faster in the naive construction algorithm. And later, for GBN, later optimization, which is short for global value numbering, we can see that it will improve the optimization result for the GBN. So if you visit blocks in this reverse post order, you are going to see the optimization result will be better for the GBN because thanks to these two properties here. So we are going to discuss it later. So let's visit this topic in the probably in the next week. Okay, so let's going back to the main topic, which is the domination relation and its relation to the mem-to-reg. And for mem-to-reg, we are going to use what is called a dominance frontier. And it starts with its definition. And the definition is that the dominance frontier of X is the set of blocks Y, which is not dominated by X. So dominance frontier of X is basically at the boundary of the domination of X. So if a Y is in the D of X, then you should guarantee that this Y is actually not dominated by X. But all its predecessors are dominated by X. So Y is, in other words, just becoming undominated by X. So all the predecessors of Y are dominated, but Y itself is not dominated. So that's the definition of this dominance frontier. So this is the meaning again. So Y is at the dominance frontier of X means Y is at the frontier of the domination of X. In other words, Y itself is not dominated, but all Y's predecessors are dominated by X, or it is X itself. So that's basically the meaning of this Y. And this idea, dominance frontier idea, is well applied to CFG and mem-to-reg optimization in this way. So first of all, the validity of a register, for example, say X, ends at its definition's dominance frontier. So suppose that this %X is defined in a block B. Then %X becomes just undominated and it becomes just invalid at its dominance frontier. The reason is that all its uses should be dominated by its depth, and this dominance frontier is just becoming undominated, and as a result, this variable X is just becoming invalid at the dominance frontier. And another implication is that if you want to prolong the lifetime of this variable X, then you need to insert a phi node at the dominance frontier. So even though the lifetime of X itself is gone at the dominance frontier, and if you want to prolong the value, you need to insert a finite that is given the value of this X, and it is going to define another variable, say X prime, as a finite that is past the value of X for the later part of the graph after the dominance frontier. So this idea, using inserting finals at the dominance frontier to prolong the lifetime of a variable, is used in the mem-to-res algorithm. So let me explain this a little bit more details. So this is all about ideas, and these ideas will be explained in the later video with a code. So I'm going to show you the code of this register promotion, explaining all these ideas presented here. So I strongly recommend you to watch this video and the code video, and then see what's going on there. So, and let's assume that X is a set of stores to a promoted location L. So L is promoted by the mem-to-res optimization, and X is the set of the stores that is storing values to such a location L. And then using this idea, if you want to prolong its lifetime, insert a finite at its DF, we know that if you want to, you may need to insert finals at the dominance frontier of X here for L, because you may need to prolong the lifetime of a location that is promoted from the location L. So maybe you may need to insert a finite registers at this dominance frontier of X. That is extending the lifetime of the registers, basically. That is corresponding to the promoted location. And in turn, these are also registers defined at some block. And the lifetimes of those finite registers are just becoming invalidated when the counterflow reaches the dominance frontier of X. And blah, blah, blah. So probably you need to insert another finals at here because the lifetime of those defined in this block is invalidated here. So you may need to insert another finals here and another finals in the df of df of df of X, and on and on and on. So this is basically the union of dfi of X. You can calculate them by using a simple iterative algorithm here. So here is an expression again. dfx is where the validity of X ends. So probably you need to insert finite registers at the beginning of these blocks. And dfx is where the validity of dfx ends. So probably you need to insert another set of finite registers at the beginning of these blocks, and on and on and on. And conversely, at the other blocks, if your block is not at this set, then the validity of stores are not ended here at the other blocks. So you don't need to insert any finals at all in these blocks. So in other words, these df union, df union, blah, blah, are the only blocks on which you need to insert finals, potentially. So it may be possible that you don't need to insert any finals here, but if you insert finals in any block, then it should either be in dfx or dfx, and on and on and on. And other blocks doesn't need finals at all. So that's the essence of the idea here. And once you calculate this set, then you are going to scan the block and deduce which finals are actually necessary and which finals should be actually inserted. So the algorithm is like this. So regard each potential finals as variables. So you may be needed to insert a phi node for a location L at, for example, Y, which is inside this dominance frontier of X. So you can represent this as a variable. Oh, this is a phi node that is potentially a thing we need to insert for location L at the beginning of Y. So let's say this is P, L, comma, Y. And you can deduce equations for the phi node variables and load results. So you use KAIST through the blocks, and if you meet a load instruction, then you are going to figure out which value should be replaced. You should figure out which value should replace the load result here. So it can either be on the result, the value of the earlier store instruction, or it can either be a phi node that is just inserted here. So if you are going to use a phi node, then this variable is used instead of the values here. So anyway, you deduce all the equations on the phi node variables and load results. And the final step is insert phi nodes only if the corresponding variable is used for the optimization results. If a load result is replaced with a phi node variable, then the corresponding phi node should actually be inserted, and then insert it, and actually insert it, and then use the phi node as the replacement of the load result. So that is basically the high-level idea of how to use this dominance frontier in the register promotion optimization. So this is the end of the slides for the domination relation. But it is, as you can see, that these slides are a little bit dense, and it doesn't have any examples. So in the companion code video, we are going to look at the code and on the optimization examples to see what's going on and how these ideas of domination relation, dominance frontier, reverse post order, and these scanning block things and all the others are combined together in the code video.